By the way, it's always useful to think about physically what's going on here. Have a good example attached to some of this theory. Again, let's stick with our runners running races. The idea is, people who run competitively, say running half marathons. A half marathon is about 13.1 miles. People who win those races tend to run those in about an hour, maybe a little over an hour, maybe an hour and 5 minutes, something like that. And then you have people who win oftentimes will run that quickly, and then you have people who come in about an hour and 15, hour and 20 minutes, hour and 25 minutes, and then you have you see a few around an hour and a half, hour and 35 minutes, and then a whole bunch probably around 2 hours or 2.5 hours. Okay, so maybe here's an hour, here is here's, well, it's not very good. Let's try this again. 0. Here's, let me make sure that I have enough space here. Here's 2 hours. Okay. So the idea is that if you're looking at maybe the PDF, maybe this is the probability density function for x1. Okay, something like that. And then maybe the PDF for x2, the marginal, is like there, and maybe the one for x3 is there. Okay, so this is the PDF for x2 in parentheses, because we're looking at the second place finisher, and this one is green. I'm going to color that green. This is the PDF for x3 in parentheses. Okay, so you can sort of think about it like that, and then jointly, what does the joint distribution look like? Okay, well that's going to be a lot more complicated. I'm not even going to try to draw that, because you'd have to draw this thing in like n dimensions. I think I'm a pretty good artist, but I'm not that good. So let's see if we can nail down the marginal for the kth largest, or I guess the kth smallest, right? It's all right. Anyway, yeah, of these guys, x sub k in parentheses. That's what that is. Well, so first of all, what I'm going to do is I'm going to multiply this by dx, okay? Because I know that this is roughly, this is basically the chance that the kth order statistic takes on a value between x and x plus dx. All right. And this is going to happen. Well, let's draw a picture. Let's draw a picture here. Actually, this can go off to negative infinity, positive infinity, whatever. Here's x. Here's x plus dx. I get the kth one in there. Kth one is going to occur in there if and only if you get k minus 1 of those random variables hitting over there, and n minus k of them falling over here to the right of this tiny little interval. Okay, you need to get one thing in here, k minus 1 things over here, and n minus 1 k things over here. And each one of these little trials is independent, right? x1 can fall anywhere on the real line according to the CDF big F. x2 also falls anywhere on the real line according to the CDF big F. They're all independent. And so I'm thinking multinomial, right? The multinomial distribution has to do with doing n independent trials where each one is of this type with a certain probability. Actually, what's the probability that it falls over here? It's just the CDF evaluated here. And then what's the chance that it falls in here? It's just going to be the common density function multiplied by dx, roughly. And then the chance that it falls off to the right, that any one of those falls off to the right over here, is just going to be 1 minus the CDF evaluated at x, or x plus dx, but they're basically the same. So yeah, okay, so need a little more room here, so I'm going to drop down. This is wasted space for no reason at all. Okay, so I've got, I'm just going to think about the multinomial distribution there. Got that funny notation, right? N minus k. That's how we can write that. The chance that it falls over to the left is f is the CDF of x, but I got to raise that to the k minus 1 power, right? And then the chance that one of those guys falls in here is roughly the joint PDF times dx, and then the chance that it falls off to the right is 1 minus f of x, the CDF f, that is, and then I got to raise that to the n minus k power. In case you don't know what this notation means, it should be pretty obvious that, I mean, what we mean by that is n factorial over k minus 1 factorial times 1 factorial. I'm not going to put it there, but there's a 1 factorial there, and then times n minus k factorial, okay, times f of x to the k minus 1 times 1 minus big F of x to the n minus k times the density function f. And then, of course, we need that little dx there. So this tells me that, in fact, the density function for the kth order statistic can be written as all of this stuff without the dx. Okay, that's the density function for the kth order statistic. And in fact, if you computed all these, if you did an example, and you know, maybe you were looking at race times or something, you would see that, you know, the first marginal density function would probably sit over there like that, and then the next one would probably sit somewhere off to the right. Okay, and then the third one is gonna, you know, might be over here somewhere, and then the fourth one, the one that describes where the other one is over there, and maybe the nth one is over here. Okay, something like that.